Okay, welcome everybody. So I'm Alistair Beresford, head of the computer science department here. So first, a quick bit of housekeeping if you're new to the lecture theatre. We're not expecting any fire alarms, but if there is a fire alarm going off, there are exits on the ground floor on both sides and also on the first floor at the top. So it's my immense privilege to welcome Bjarne Stroustrup back to Cambridge today. He's someone who's a long-standing dedication to the design and the implementation of C++, and I'm sure that's familiar to many of you here. He's received numerous awards for his work, including the Grace Murray Hopper Award from the ACM, the Charles Stark Draper Prize from the National Academy of Engineering in the US, and the Faraday Medal from the Institute of Engineering and Technology here in the UK. He's a fellow of the IEEE and of the ACM, and in fact he has many, many accolades, too numerous to list in one introduction. When I was reading up about Bjarne's history, I came across a lovely piece from 2018 when he described his very personal story as someone who was the first in his family to finish school and indeed to go on to university, who currently felt unable to travel far from his home, studying at the University of Aarhus. But after that, he took the opportunity to travel not just elsewhere in Denmark, but indeed came to Cambridge to study for a PhD. He then spent 24 years at Bell Labs in the US, where he designed and implemented C++, and then on to Texas A&M, where he was a distinguished professor. He returned to industry as managing director at the technology division in Morgan Stanley in New York, and most recently returned to academia as a professor in computer science at Columbia. Really an incredible career, and one that speaks to the power of education to unlock dreams beyond imagination. In amongst so much of this, there is one constant, and that is C++, something he continues to take and devote his time to as his project. And I'm very much looking forward to hearing today about concept-based generic programming and where he thinks C++ is heading next. Bjarne.
Okay. Thank you very much. I work with programming languages, but more with programming. Languages are tools for expressing ideas and to make it easier to express ideas. And that's what I'm going to talk about today. I'm going to talk about generic programming and the version of generic programming that you get in C++. They started out mostly designed by Alex Stefanov, and if you want to know the mathematical basis of all of that, there's two books there on the screen about it. That one is very heavy on math. That one is the heavy on the history leading up to it, according to Alex. So he has a slight modest aim for generic programming, the most general, most efficient, most flexible representation of concepts. Concept is just another word for idea. So this is fairly ambitious. And he has some rules of thumb. Don't abstract for just for the sake of abstraction. I found talking in France, that everybody knew that abstraction meant bloat and complexity. It's exactly the opposite. When you abstract correctly, you get a simpler way of expressing an idea. And abstraction comes, when you do it well, from something concrete. You have a concrete problem or a set of concrete problems, and you generalize to a solution to those problems. And to be useful in the context of programming, you actually have to maintain performance. My interest in programming has a lot to do with areas where performance, reliability, energy consumption and such are optimized. So that's what I'm very interested in. My contribution here, my work here, is actually to make this feasible in the real world. Represent concepts separately in code, combine concepts freely, minimize overhead, and actually make programming with the generic code as simple as non-generic code. Actually, I will argue I can make it simpler. And we're going to look at a problem because you can't discuss principles without examples. And I articulated some principles for what I wanted back in the late 80s, early 90s, wrote it up in a book called Design and Evolution of C++ from 94. I wanted generality, uncompromised efficiency, and statically type-safe interfaces. Now, there was just one slight problem here. When I wanted to do that, I couldn't do it. I tried, I walked around, talked to experts all over the world in these kind of things, and I couldn't get all three. I got generality, I got uncompromised efficiency, meaning I could compete with C successfully in systems programming. Generality, you have to be able to express more ideas than I can imagine. Obviously, in a group like this, people have more good ideas than any individual in the group. But I couldn't also have it statically type-safe and maintain efficiency. It was not that hard to get type-safe interfaces to generic code. All you need is a whole bunch of indirections, indirect function calls, indirection to data, and I couldn't afford that for hardcore systems programming and embedded systems and such, so I couldn't do it. But now I can. This is what I'm going to talk about today. And there's some further constraints on the solution to the problem. It has to be affordable, both in terms of computers and compilers. It is not something that you should need a fantastic amount of money to get done, or you have to drink too much coffee waiting for it to compile. And it has to be teachable. Christen Nygaard, who's the inventor of object-oriented programming, expressed it as, if we require PhDs from MIT, we have failed. There's nothing wrong with PhDs from MIT, but there's not a supply to generate all the world's programs. They're in short supply. So these are the constraints on the problem. And here comes the problem I want to deal with. I've been suffering from the rules for conversions of the built-in types in C for, well, 40-some years. I tried to fix it when I started C++, but the people at Bell Labs, including Dennis Ritchie and Brian Kearney and such, said that no way I couldn't mess with that. Anyway, so what I'm trying to say is that using generic programming the way it is expressed now in modern C++, I can solve this problem. And here's some examples of things that we don't like, the problem. If you take a large integer and assign it in a small integer type, you lose precision. If you take an unsigned and turn it into a signed, or a signed and turn it into an unsigned, in both cases you can get the wrong answer. I mean, if you take a signed number and assign it to an unsigned, it shouldn't work. But it does. You get a very large signed number. And negative integers can be large positive values after conversions. There's the unsigned x equals -2. That's legal C. It's legal C++. And obviously, x there is not an unsigned, is not a negative number anymore. This should never happen. Floating point numbers, you can lose the decimal part. And these days, there's a lot of floating point numbers that has a very small mantissa, because they're interested in a huge range, and precision doesn't matter too much. If you're just drawing some colors on the screen, or if you're doing matrix multiplication for LLMs, you don't need much mantissa. So the example down there that lowest x bfloat 16, that's a type supplied by the Intel machines. assign 300 to it, and you're going to get the wrong answer. This is not good. You could design a whole new language and not have this problem, but if you design a whole new language, you have to get people to use it. There's about 7 million C++ programmers and a few billion lines of code that wouldn't work anymore. So let's deal with that within the context. And the solution is to express it in terms of concepts. A concept in this context is a compile time function that can take types as arguments. So there, with the notation we have, the concept num, a t is a num if it is an integral or if it is a floating point. Those integral and floating point are compile time functions in the standard, so you can just pick them up and use them. For some reason, historical, instead of using round parentheses, we use sharp parentheses to indicate types. That's just the way it is. I copied that out of some theory books back in, in the mid-80s, and it's too late to change anything about that. So anyway, here we have now defined num to be either integral or floating point. We can extend this later if we also wanted non-standard types like big num or something like that. But for now, let's just stick to what the standard says. And now I want to define which conversions could possibly narrow. Narrow meaning losing information. So I really want to know whether when I take two types, here I'm going to take can narrow to a t converted to a u, can it lose information? Because I don't want to go and check things if it couldn't possibly give the wrong answer. So here we can read this as perfectly ordinary code. So first of all, if t and u is the same, there's no conversion, so I don't have to worry. If they are not both numbers, they can't narrow because they can't get into this. Then I can check floating point and integral. If I'm converting a floating point to an integral, I will lose the decimal part. And I can take numeric. I can take, if the size of the mantissa isn't large enough, I can get a truncation. And there's a very strange rule in C and C++, which says if you have a signed integral and an unsigned integral, and their sizes are the same, you might actually get a problem. So this problem is very carefully and detailed designed on about 3 pages in the C and C++ standards. So the first thing you see here is I've turned it into code, and it fits on 7, 8 lines, depending on how you count. We've formalized what in English is a couple of pages. And anybody who claims they understand all of this are probably wrong. There's a few C compiler writers who get this right every time, but most of the time we don't. So complicated logic, but it is now so compact that we have a chance of actually understanding it. And then I want to know if a conversion really will throw away information, will narrow. And that involves looking at a value, not just the type system. So first, I'm going to test whether they can can narrow at all. Because if it doesn't, it won't. If it can't value, it won't. Next, I'm saying whether they are integrals and unsigned integrals, and I test whether the signed integral is bigger than no, wait a minute. I'm converting to an unsigned, so I have to. What on earth is going on here? If there's bugs, it's because I can't copy from the real code. Okay. T into U, unsigned. The T is supposed to be the unsigned, and down here it's the opposite. Apologies. So basically, if it's a signed turning into an unsigned, we have to check that it's not negative. That's what I'm doing here. And if I'm turning an unsigned into a signed, I have to check that it's not too big. Okay, if all of this, so I first check things that can be checked at compile time, and I only do the runtime checks if it is possible to make the mistake. I test these things that in the standard, and if not, I am converting the T to a U, and then I'm seeing if the value has changed. That takes care of floating point and things like that. Oh dear. I wish my compiler could compile slides. Anyway, then we have to do something, decide what happens if we convert, and basically there we say if it will narrow, I'll throw an exception. Basically, I don't want narrowing, I don't want to lose information at all. And if not, I can convert it. Fine, done. And I use exceptions here because in real code, in tested code and such, this is extremely rare. And this is where we want exceptions for exceptional things. Now I can write code like this. I try all kinds of things. It's a bit of test code, a small part of test code. I try big integers, little integers, unsigned, floating point, the works. I can do this. But you know, this is not real code. There's no way we can get software developers to consistently and correctly convert using conversions. The language allows implicit conversion, so the compiler wouldn't catch it. So I look at this. We can now do it, but realistically in the real world, people won't do it. So let's define a number type that does this implicitly. So here I have got a number type number. It holds a value of a numeric type, and then you have the constructor that constructs from something, and we check convert to when we take the value to store it away. And we do the same for assignment, and if we want the value, you just extract it. All of this, by the way, in the standard C++ compilers that people use it, if you use -02, all of this disappears except for the code that must be checked. We've taken care of that. And now I can write code like this. I have a number of unsigned, a number of char, and I can try things, and here it's another test. I'm trying to break the system. No, it will catch me whenever I try to do something I shouldn't here. So this is a almost 50-year-old problem. And if you count the number of lines of code that I just showed you, it's, I think, 42 lines the way I indent things. It would be less if I didn't use industrial style indentation. So that's not bad. Furthermore, it guarantees that you only do a runtime check when you need to. Things like assigning an integer to an integer or assigning a char to an integer will just work. Okay. But we have to go a little bit further, because what a numeric type without numeric operations like plus and multiply are not very useful. So I'm defining first something called a common type. It's common is standard common type. We have in the standard the notion of taking two types and see if you can promote them to a common type so that you can do operations without special rules and such. So I'm just converting them to their common type and then doing the operation. This is just boilerplate code. We do it with plus, minus, divide, multiply, you name it. And very importantly, we have to deal with less than and with such. In C and C++, minus 1 less than 2 unsigned is false. Because the rules of the language is that you promote to do mixed arithmetic of unsigned and signed. You promote the signed to unsigned, and converting minus 1 to an unsigned number, you get close to the biggest unsigned number. So obviously it's not less than u. Again, looking at the problem, how do we solve it? Just define a a less than operator that uses nums rather than the built-in signed and unsigned. And so basically if one of these values are less than 0, then of course it's less than the unsigned number. I mean, the arithmetic I'm doing here are very, very simple, usually a single operation. And there's the minimal number of tests, because tests slows down modern computers. Okay, and now I can write code like this. You take a mixture of ordinary numbers and numbers that I've defined, and they all get promoted to nums, so they check for narrowing, and then it does what it would have done with the normal types, provided that they didn't make any mistakes. So guarantees that we won't get the narrowing conversions and minimize the number of tests being done. Okay, now one reason I'm looking at this is I was looking at the bug reports to some of the big companies on Earth. And one of the problems that you have is range errors. You subscript with something that's out of range of what you're subscripting into, and then you get an error. It is also a favorite of hackers that wants to break in. And I found, and was told by people who can look into the details, is that a very large number of these range errors happens because people have indices that are a mixture of signed and unsigned arithmetic. In other words, you fall into the kind of traps I showed you before. So if you thought it was just bad but uninteresting, it is what breaks your computer when it goes really bad. So let's look at an example here. I have an unsigned max. Some people like unsigned a lot, I don't. But anyway, we take an integer array of max, and then we take a span, which is basically a subrange. A span is a pointer to a beginning and a range so that you can do range checking. Okay, on the other hand, I'm a bad typist. So my finger slipped, and instead of saying max minus 50 to get the first half, I got max minus 500. Now, thanks to the rules of C and C++, that max minus 500 is a very, very large number. You see it there. You see it there. It's that big. Now, SPAN does range checking. At least my SPAN does, and it's always going to work. They're never going to catch an error there. And this is the kind of errors that happens when people use subscripts into various structures as spans, as vectors, as standard library arrays and such. So this is actually a fairly serious bug. Ask the security people at Google or Microsoft and such. They really, really don't like this. So we're trying to deal with it. So I'm going to make a concept for a container, something you can subscript in. And let's start with something that works for arrays, built-in arrays, vectors, and such. I define a concept which I call spannable. There is a library in the there's a concept in the library, a standard library called contiguous range of S. I'm just giving it a name because now I can extend it to things that are containers that I might want that isn't in the standard. But also because I'm a bad typist, so just saying spannable is simpler. So I'm going to define a span that cannot suffer the range problems. So I have a check here. If I'm going to test subscript with n, I see if the subscript is less than n, which is the size of the range. And if it is, that's an error. And I can now construct spannable out of a data and a size, which any spannable is supposed to have. Contiguous ranges have them. And when I extract it, when I extract the value by subscripting, I make a number out of the subscript. I check it. Since I'm now using numbers, I'm going to get protection against narrowing, and this sort of works. And there's a very simple span for doing that. And you get the tests if and only if you are mixing signed and unsigned, or if you are daft enough to use a floating point number as an index and such. And we can do things like this. Here I've got a span of a number. I have a vector. I try to do these things. Again, I'm subscripting. It's okay. I'm subscripting with a negative. No, it'll throw. I'm doing. That was, yes, SSI is one of my spans, right? I can have a local one, it works fine, it's obvious. One thing I should point out is that the compilers will catch obvious errors. If you assign -1 to an unsigned, the compilers will complain. The point is that the simple cases are caught, but not all cases simple. So what you're really doing in many cases to get into trouble is you take a subscripted value from one area and use it in another area. Now a static analyzer can't find the problem. You really need dynamic checking. A compiler cannot handle that case in general. Okay, it works. Now this span is let's see. Oh yes. Let me just show you something. I keep having to say span of something, but we have something in C++ called type deduction, which the pretentious people in the standards committee like to say class template type deduction, and then immediately abbreviated it to CTAD so that they can show they're cleverer than you. Anyway, so we want to get rid of this. I'm just saying to the compiler that if I have a spannable and I initialize it with span of R, a reference to something, I of course want it to be a span of the element type of the thing I'm spanning over. I mean, the compiler knows this. A lot of what I'm saying here is the compiler knows it. Let's give people a reasonably easy way of using what the compiler already knows. There's people who like to say things again and again and again, but that gives opportunities for mistakes, in my opinion. So let's ask the compiler, it knows. And now I can write code that are just sort of what we would like. We have here an array of 100 integers. The span deduces that it's a span of integers, and it looks in and finds that it's got 100 elements. So it's now a span of 100 elements, and I can now go and use it for each x in this span do something. So I don't even go and subscript anything as I would in old style code. Here I've already told it what this range of elements are, so I can just ask it to use that. Now, unfortunately, this is slideware, so we have to have a more realistic span. For a span, you just don't want all the elements of a container or something else. Sometimes you want the beginning, the first half or something, and sometimes you want a sub-range in the middle. So we'll do that. That takes another page of code. Basically, here I have 0 to nn initialized like this, and I have low to high, which is a little bit more complicated because you have to check that low is within the in the range, and then you have to check that high also is after you have moved the span. But again, this is something that is fairly easy to do. By the way, I wrote a paper about that. You can find it in my publication list on my website, and it doesn't have the bugs that I was suffering from earlier, because there I did copy out of the code more directly. Anyway, the more realistic span, again, we have to tell it what the element type is. So if you're initializing with a range and an unsigned, it takes the ranges value, same with subspan here. And then there's this problematic thing here. If you have a span of a pointer and a range, you pick the span of the element types. The size isn't there. We are now in problematic territory. This was this constructor here that I skipped when I was explaining things. It gets a pointer, and it gets a range, and it initializes it, and there's no narrowing problems here, but it could be the wrong type. And these are the things you get all the time when you're doing things like communication with buffers and things like that. But this one cannot be statically checked, or you get pointers to elements coming out of the operating system or something like that. So this one is very realistic, and it is not statically checked, statically safe. So the point here is that if you see one of those, which you do here, down at the bottom, all of these are checked properly down to here. Here I have a pointer, it comes out of somewhere, and I'm saying I want the first 10 elements of it. I don't know it has 10 elements. So I can't check it. The information is not there. And so what I'm actually doing is right here, I'm giving it the size. And this stands out for humans, for code reviews. Static checkers can trigger a check on this, but we can't provide the guarantee. If you want to deal with raw memory, you end up here very quickly. And by the way, at this point, I'm starting to wonder why, when I'm talking about num, do I have to say num of unsigned and num of float and such like? We can just invite a deduction here. If I have a number of an initializer, make it a number of the initializer's type. Of course. And now I can say number n equals 1. And 1 is an integer, so that is a number over integers. Number 2 here is 1 unsigned. It's the number of unsigned. So if I start mixing n and n2s, then I'll get checks. And here's the number n3. It's 7.2, so it's a number of floating. And if and only if I want to have a number that is not the type of the initializer, well, I can just say so. In other words, if I just want to follow the default rules of the language, I can. I don't have to say anything. The compiler knows what type 1 is. But if I want something else, like initializing a double with an integer, I have to say what I want. So this, we now have num and span fairly realistically in the way people write code, and actually writing as much code as people, no more than what people actually write with the built-in types. So what I have done here is I've extended the C++ type system using maybe 100 lines of code to eliminate narrowing conversions and most buffer overflows, most range errors, and made the potential problems stand out so that my static checker can say, well, I don't know if this is right or wrong, call a human. Flag it as a potential problem. That's the best you can do. Okay, so let's go back. When people talk about generic programming, if you go to Alex Stefanov and most other places, my textbook and such, the standard example of generic programming is something like a sort function. And I'm going to show the sort function as it is in C++ 98, and then I'm going to improve it till some major problems have been eliminated, mostly using concepts. So here is what we start with. We say that there is there's a function sort. It takes an iterator and another iterator, and those iterators have to be of the same type. You read the manual and it says these things. Good. This was spectacularly successful. It was one of the things that for generic programming was used more widely than all other versions coming before it. This stuff did not invent generic programming, but it spread it by at least an order, probably 2 orders of magnitude. That's success. It's efficient. You cannot handwrite things better. It's flexible. You can do amazing things with it. And the error messages are spectacularly bad if you make a mistake. If you don't make a mistake, everything's fine. So let's test it. We sort, saying I want to sort from the beginning and the end to the vector. Remember, we can do sub ranges and things like that. I can do that for a span also. And then I try to do it at a list. A list will not follow the rules of the type. The type, as it was on the previous slide, I explained what is said in the standard. It has to be a random access range. and it had to have a less than operator. Lists do not have a random access. Lists are not very good at for sorting. They're slow for traversal and things like that. So this actually, if you look at it, violates one of my ground rules for generic programming. It has to be reasonably checked, statically type safe, etc. It's statically type safe in the sense that it gets caught eventually, but it's not good enough, it's not precise enough specified. So we can use concepts to specify this. It says that I want 2 random access iterators. And a random access iterators was defined earlier in the standard and then in code here for random access iterator. And then I have a predicate for testing whether things are less than, how to sort things, the sorting criteria. And I can do that. And so now we have this definition of sort, which is very specific. It takes a random access iterator, it takes a predicate, which is defaulted to less, and then the combination of the iterator and the predicate must work together. Basically, the elements of the sequence must be something that you can compare to each other using the predicate. Fine, so that is done. The difference between this and the previous example is simply that it's checked up front so you can get decent error messages and you can do overloading and other good things with it. So basically it's same performance as we've always had, and we just get sooner and better error handling. So we can do the old stuff without changes. This is important. There's a few billion lines of this stuff out there, so we don't want to mess with it. But I can now also do things in descending order. And now, if I try to sort the list, it will say the list doesn't provide random access. I had a prototype 10 years ago that actually literally said that list does not provide random access. The current implementations of the compilers are a bit old style. They're a bit more verbose than this, but the information are there for that. And it's not just a conjecture, I've done it. So there's more problems remaining. Again, look at code that is in the real world and see what mistakes people make. And this one here, you flip the vector end and the vector begin, and you get something truly horrid. I mean, you're trying to get from here to there. It's just bad. Or you take one container's begin and another container's end. People shouldn't do that. People do that in the real world. Logic errors are at least as common as type errors, especially in tested code. Anyway, it's also verbose. I have now, for decades, disliked having to say sort of v.begin, comma, v.end. Why can't I just say sort of v? And the answer is that overloading didn't work too well without having the types of the arguments properly specified. But now, with concepts, I can just define the right concepts and then overload on them, so that we can now get the old stuff with iterators and the new stuff with ranges. So that now looks, I introduced this one in addition to the one with the iterators. And concept of sortable range is a random access range. Again, I'm using the standard. It's there. You don't have to write it yourself. And it is sortable with that predicate and the iterator that the range must have. Problem solved. So this is just programming, just ordinary programming, and it's 2 lines. It's not not difficult. The syntax is a bit unusual, but we get used to it. I know, I've gotten used to it. Anyway, and now I can then start sorting ranges. Here I wanted to implement the sort function for a range, and I implemented it by calling the sort for the iterator version of it, and the overloading will make sure I get the real one. And well, I mean, that's fairly simple. And what if I did want to sort a list? I mean, it's very doubtful that I want to sort a list without saying list anywhere. It's fine to sort lists. There's good algorithms for sorting lists, but having having a simple way of just saying sorted or subscript a list gives really bad performance in some cases, so we don't want to go there. But if I wanted to go there, just to demonstrate what we're doing here, I can do it. I define a forward sortable range, which is slightly different than the sortable range, simply because it takes a forward range rather than a random access range. A forward range is something you can traverse. That's it. And now I can implement my simplest implementation of the sort of a list, actually anything that can do a forward range, copy it to a vector, sort it, and copy the elements back again. Unless you are really into heavy performance and very large data, this one works rather nicely. Well, it works rather nicely, but it also works rather fast. You should try it if you doubt that statement. And so overloading picks the most constrained function. And we don't have to define hierarchies of priorities and something like that. So if I now have a vector and a list, and I sort the I sort the list, only the forward range version of this list will work. So obviously we pick that one. If I want to sort the vector, it figures out that I could do it with a forward range, and I could do it with a random access range, and it picks the one with the most stringent criteria, the most demanding criteria, because the assumption built into the language here is that if you require more properties of a type, you can do better things with it. So that's how this works. So you don't have to have type hierarchies or class hierarchies or constraint hierarchies, none of this stuff, just perfectly ordinary functions with the simplest overload resolution you ever saw. If there's only one thing that works, you pick it. If there's no thing that works, you don't pick anything, it's an error. If there's two that picks it, you check whether the two are subsets of each other. If they are not, it's an ambiguity, it's an error. If one is a subset of the other, pick the one that is the most stringent. End of overload rules. If you've seen the overload rules for C++, you'll appreciate how simple this is. Okay, so concepts. I've been talking about concepts, using them. I'm using it in the way you, I'm explaining this in the way you do natural languages. There's two ways of doing natural languages. One is you first teach people the full grammar and the dictionary, and then you start saying things. That is a lousy way of learning a foreign language. Here, you start talking, you show how you can say things, and then later get to the details. That's what I'm doing here. We've always had concepts, we being the C++ community. The C building types, you read Dennis Ritchie's and Brian Kernighan's book from 78, the rules came in 72. There's two concepts, arithmetic and floating, and they are specified in the manual, not in the code. We have STL, Standard Template Library concepts. That's Alex Stefanov's work. Iterators, sequences, containers. Math has had concepts for a long, long time. We had monad, group, ring, field for a couple of centuries, at least since Abel. And graph concepts we can pin down. The bridges of Königsberg introduced the concepts of edge, vertex, and graph, not DAG, but anyway. This is not, the notion of concepts is not new. The fact that we can use them in code very simply, they are just functions that happen to be able to take types, is new. And we've always had concepts in people's heads and in manuals and such, but I want them in code. Let's see. So concepts are built out of other concepts. I showed it with the num type. I showed it with the forward sortable range. They're just built out of that with a slightly different context. Now, that is just the way we write code. I mean, we usually write code using, when we define a function, we use other functions. If I want to do a square root, I don't write a square root algorithm. I haven't done that since I was an undergrad. I use the square root function, and we do that again here. But sometimes you have to go and do the define a concept in terms of the language itself. And for that we use what's called use patterns. And so here I'm saying that the concept equality comparable of a T and a U, you can do, you take a T and a U and then you simply write a use pattern. I must be able to compare A and B with equality, with non-equality, and B and A the other way. I can simply write those patterns, this much work. This says what you must be able to do. It does not say how it must do it. It does, and it says, by the way, that the result has to be something that's a Boolean, something that you can use as a Boolean. So this will work for old-style code where they're using a Boolean type that's really an integer or things like that. It's more general than what you get in the language. And in C++, you can define equals as a member function or a freestanding function. It will all work. It just says what a user can rely on. Here's the examples of different ways of defining a plus. I can say that my code requires that I should be able to add things. It doesn't say anything about how the implementer of various types has to do it. It can be built-in types, it can be user-defined types, and there's various ways of doing it. It also gives API stability, because if somebody changes the definition of operator plus, once I recompile, it'll check that it'll work, and it'll work. And this handles mixed mode arithmetic, it handles implicit conversions. Lots of languages have constraints, things that can't do that very well. That we had an attempt in C++ to define constraints in terms of a constraint class. It couldn't handle mixed mode arithmetic implicit conversions easily. This is trivial. It's just you call a function to see what it does. And if you want to test whether your type actually matches a concept, you can just write it. We have static assertions in modern C++, basically assertions that are tested at compile time. So here I am saying that I'm asking if if int is equality comparable with double. Of course it is. Is int comparable with itself? It is, and I think I spotted a bug. No, I didn't. If you only give it one type, I default to the first one. And that is actually one of the most common cases that you're having a homogeneous type and operations. So that's fine. And finally, I can try and see if int and string are equality comparable, and the answer is no. So the static assert was not equality comparable. So for types you can test in advance. But when you're writing a piece of code, a library or something, you don't know all the types that's going to be used. They will be checked when they are used, and that'll just work. This is an open system. Then I'd like to argue that generic programming with concepts is an integral part of C++. And basically, I started working on some of the prerequisites of that back in '79, and the use patterns I showed you is we have a Pobble paper from 2006, and this has been going on for a long time. I'll show a couple of examples, but the idea is that generic program is just programming. And so the beginning was that some languages like Simula, or also now Java and such, distinguishes between built-in types and user-defined types. And they want you to use new for a user-defined type. If that was the case, I couldn't interchange built-in types and user-defined types. And really, in the earliest days, I couldn't see why there should be different rules for int and complex, just because Dennis invented int and I invented complex in the language. And I used the library function. So the fact that this works is the beginning of generic programming. It is actually even more interesting because resource management is built into C++ types. The rule is if you want a resource represented as a type and use that type, like a file handle or a smart pointer or something like that. So I don't have to use this, remember whether I have to close or relinquish or something of the type. It all just works. Okay, and one of the things we have a lot of is optional member functions, like a smart pointer has to have an optional operation which is dereferencing, and it should work only if it's a pointer to something that's a class. Here's a classical example. I have a pair that you have in the standard, and that's a pair of a T and a U. And you can take another pair of a different T and a different U, and I can initialize or assign the one to the other, provided you can do the conversion. And then I looked at this. Convertible to is a standard concept. It is a concept now. But anyway, this doesn't protect me against narrowing. And so I looked at this and said, I can do better than that. So what I'm going to do is I'm going to say I can assign a TT and a U pair to a T and a U pair, provided I can convert the T to the U, to the argument T to the thing I'm referring to, and that's argument U to the type I'm referring to, and I'm getting the protection against narrowing right there. And this is one of the things that this is my aim and I like. Notice that this code is slightly more complicated than that code, even though this one does more and has significant less chance of errors. The only problem is that this one doesn't work. Because I can have a pair of an integer and a string, and I defined convert to take only numbers. I did mumble something about extensions when I did the numbers, because I knew I was going to get here eventually. But still, we have overloading. We can overload on concepts. So we will get the num definition of this if t is a number, and we can just define ourselves a new convert to. And since num is more constrained than this convert to on this slide, it'll be picked for numbers, so we'll get range checking, and otherwise it'll check whether it can convert. And the curly brace notation is a part of the language that says it should be possible to convert. So if I have u being a string and t being an int, it will not work. You'll get a compile time error. Okay, but it'll work if you convert, say, a C-style string to a C++ style string and such. The overload rule cuts in, and I can just extend the system like that. Whoops. One of the things that bothered me about generic programming and C++ in general was that people, over my almost dead body, enforced the rules that templates had to be defined up before you use them completely. So you get them in header files. This, by the way, is one of the reasons that traditional C++ runs rather slowly. And then in C++20, we finally got modules, which is things that can be precompiled and used just like any other code. And so here's a module. I'm exporting the map print. I'm defining a module called a map printer. It imports all kinds of good stuff that I need for the implementation, and it does not leak it out into the rest of the program. It is just implementation details. Only what is called export is exported, is available if you import this module. And so I defined a template, a map printer that prints anything with the key and value pair. You can look this up. It compiles rather fast. I reckon that if you use modules rather than includes, you will average about 7 times faster compilation. I have seen 0 to 100 times. For instance, when I use the standard library, always import std. Import the standard library. It is much faster than just importing I/O streams or something like that. Even though there's 10 times as much information I'm getting. Fine. But the point here, in context of generic programming and concepts, is that the code is now identical whether it's a template or not. You organize it in the same way. If you say import map printer, you don't have to know what is a function in that module and what is a template. It's the same. Okay, so now we're going to go a little bit into the future. We're getting something in C++ 26, actually. We're almost certainly getting something because it's being voted on now. It's not in yet, but this one will pass. So basically, this is where you can ask the compiler about just about anything the compiler knows. So I'm going to take a simple example here, which is to generate a map for a class. And this is a data member descriptor. I want for any class, I want the name, I want the offset of where the member is, and the size of the member. I know a lot of real-world large projects that need something like this. Sometimes it's functions that you can call, sometimes it's there's all kinds of stuff you might want, but you need to ask the compiler about things like names and things about the type. And so what we have here, this is not science fiction. You can go into Compiler Explorer, also known as Godbolt, and test it out yourself on the web today. And there's 2 versions of it, one from Clang and one from EGG. So there are 2 almost complete implementations of what I'm talking about now. I'm not into science fiction, except I love science fiction, but that's not what I'm doing here. So basically, this funny double up arrow here says ask the compiler. Get the metadata. And here I want the non-static data members of what you know about S, the type S. There, type S. And I want to get the layout. Once this information is now available, I can then make an array of the right size of these members, because I got the members gives me an array of something. And then I can go through the stuff I got, the metadata, and say, well, give me, make a layout of the identifier, the offset, and the size of. And once I know that, then I can export this this data structure I just created. And by the way, I've been talking about compile time functions. For concept is a compile time function. Well, you can also do that for ordinary types. This is a const eval. It says this function here has to be computed at compile time. There's no information that I used there that I can't use at compile time, so the whole thing can just be there. By the time the program starts, the layout function, the layout array is available. And I take a struct S, I ask to get the layout, and it will tell me that the layout of A is it starts at 0 and there's 1, the size is 1 and so on. Next year. But now you can start experimenting with it and start thinking about it in an academic sense. I'll just go through some major design decisions about how this all came about. I can't do everything, but there's a paper about it also. So concept of functions, I wanted flexibility, I wanted generality, and I want cheap compile time. Full templates doesn't do all of that. And we have to have use patterns to be able to write things in terms of the language itself, like that equality comparable with using the use patterns. And that handles mixed mode arithmetic and implicit conversions. That's the important thing here. I have tried to teach engineers to not use implicit conversions between int and floating point and such. You get kicked out of the office very quickly. So we need something like this. Concepts can have multiple arguments. So a concept is not a type of type. It's a function that takes a bunch of arguments. If you want something equivalent to a type, you give it one argument. I find that about half of my concepts takes 2 arguments. The argument being that if your function takes 2 types and you want to make it generic, it needs a concept that tests how these 2 types interact in your code. If they don't interact, it shouldn't be one function. And about half of my concepts, maybe slightly half, more than half, takes more than one argument. So this is not type of types or type classes or any of that stuff. And concepts can take value arguments. Let's see, here's an argument about, here's an example of that. I want to constrain a buffer type. And I need to know two things about my buffer type. I need to know the type of elements in the buffer and how many there are. Imagine me laying out a buffer somewhere. And I want my buffer space to be at least 1K and elements, and to be a power of 2. So I define a concept, buffer space, that is larger than 1K and the power of 2. And then I can say the buffer requires a buffer space. And I can use it. 100 is not enough. 1,000 is enough, but it's not a power of 2. And a buffer of 2,048 integers is okay, passes that. And by the way, there's the const_eval function for the power of 2. You have essentially the whole language available for writing your const_eval functions. It's just an ordinary function that is required to be computed at compile time, just like a concept is. Okay, talking about this, I got a lot of questions about whether this was better or worse than classical object-oriented programming. And in my opinion, they are complementary. They are not alternatives, because there are some things that object-oriented programming is really good at, that generic programming isn't as good at, and vice versa. So classical object-oriented programming, you think about what is a type of an object and what is a class hierarchy. It applies to one object at a time. It requires on names. Runtime selection is on an open set of types. I can write a piece of code and then add a new type through dynamic linking, or just because I wrote it tomorrow, it'll still work. Inlining is very, very difficult because the set of types is open, and defining an interface requires a lot of foresight. For instance, I tried many times to define a container abstraction in the object-oriented programming. You have a base class container, and then you derive vector and list from it. I never was able to do this well, because Lisp has a set of operations that it must have that works, and it has some that shouldn't, like subscripting. And vector has exactly the opposite. And now I have to get into complicated things and throwing exceptions if you call the wrong function and all kinds of stuff. And once you build the hierarchy, things get worse. That kind of stuff is trivial with generic programming and concepts. It focuses on a function's requirements on its arguments, with a plural, and it involves relationships between arguments. It relies on use patterns, which are basically usage structural equivalent as opposed to name equivalents. Inlining is very easy, and one of the key things to the performance of C++ is that we can inline and we can use compile time information. People keep asking me how much faster C is than C++. It's a wrong question, because on average C++ is faster than C, because it has more information to work on. And if you write decent C++, it'll outperform the closest thing you can get in C, even though C keeps absorbing ideas from C++. And basically, if you want classical object-oriented programming, you can get stable interfaces, ABI compatibility. Generic programming doesn't. It gives API stability, but it doesn't give binary compatibility. So they are complementary. And here I have an example. This is a classical example for object-oriented programming. Draw all shapes. I mean, I borrowed it from Chris Nygaard. And I've heard people say they'll never want to see this one again. But I think this one is different. So I want to draw all of a drawable range. I'm not saying what type it is, I'm saying it has to be a type that's drawable. And therefore, I can now say for all p's in R, draw p. And now I can define drawable range. It requires that there's a draw function that you can access with an arrow operator. And then I define drawable range as something that's drawable. This one I can now call in the classical object-oriented sense with anything that has, with a pointer to anything that has a shape there with a draw function. I can also call it with a set of unrelated types that all happens to have a draw function. And I can draw, say, draw a unique pointer to shape, and therefore get resource management and resource maintenance in place, or shareable pointers, or something like that. This is far more flexible than the classical object-oriented programming. But it is object-oriented programming because it takes the classical case also. And it's also generic because, well, a lot of stuff here is generic. Once it takes a drawable range, it's generic. Concepts can be partial. We very soon figured out that writing concepts was not hard. You just start doing it. But getting a complete and perfect concept is hard, just like getting a complete and correct base class was. So we start with something like this here. I started with a wrong button. Hey, I can do this. This is a new toy. So I wanted to be, for a number, I wanted to add, subtract, and this will catch essentially all errors. But it's not complete. I have not said that you could copy it, that you could move it, and things like that. But this is the way it happens once you start writing something. You know what you want, but you don't know everything you want. And so you can start with an incomplete. So in other words, a concept can be a partial constraint as opposed to a complete one. That allows debugging. And then this number is different from the number I showed before. This one just take t and u, and it also, I can then define arithmetic as things that takes t and u and u and t. And one thing people complain about with this is that what if you have two types that are semantically different only? They have the same syntax, but they mean something completely different. One example is that you have a plus that works both for a number and for a string in C. And that was in C++, and that was a mistake they copied when they did Java, by the way. I think that's a mistake. I made it, but somebody copied it. We can put constraints on things to take care of that kind of stuff. But there are a few problems. What if you get the wrong one? Most of the time, you don't get the wrong one. What is the likelihood that this one here, even though it's incomplete, will match something that isn't a number? About 0. You can also get false lookups by looking for something in a library, by looking something from dynamic linking, So here we have at least as much checking as you get for type lookups. We just have to handle a case where things are only semantically different, but having the same name. And in the standard, we have a forward iterator and input iterator. They both allows you to traverse in one direction, but traversing twice on an input stream gives you different results. If you want them to be the same, it has to be a forward iterator, which you can traverse repeatedly, which is a very useful feature. And the solution is to make them introduce a slight syntactic difference. In the standard, that is that a forward iterator must have a forward iterator tag member, and input iterator must not. And that trick can be done in a variety of ways and handles essentially all of these things. This would be a very nasty theoretical problem, but it has a very simple practical solution, so I went for that. And definition checking, finally, this is my last example. I, like just about everybody else, thought it was important to be able to compile templates in isolation. And then we noticed there was problems. There's a function advanced here, which is a simplified version of a standard library advanced function. It takes an iterator and it goes n elements over. And there's a log function inside that shows it's been used, and it uses plus n to get over there. There's a couple of problems here. Input iterator does not have a log function. Why should it? And it doesn't have a plus equals operator, because a forward iterator can just go one element at a time. The problem here is that a lot of industrial code has things like log functions, debug functions, telemetry, use counts and things like that. And they have nothing to do with the main use of the function, their infrastructure. And so if I wanted to have log there in a standard functional programming language, I would have to change the interface and introduce this infrastructure thing in the interface. You don't have to do that in C++. We never had to. So there's lots of code out there that looks a bit like this. Furthermore, plus equals also work there in some cases. So if I take advance as defined here, and I have a vector, and you invoke the generic function advance on iterator that happens to be a vector iterator, then it figures out that it is not just an input iterator, it actually is a random access iterator, and it can go over there fast in one hop. If I compiled advance in isolation, I would not be allowed, I wouldn't be able to do plus equals. A compiler would stop me. And then I would have to go jump, 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 jump. And that has the net effect that some of the standard library functions defined by Alex Stefanov will turn from ON to ON squared stuff. So I and others decided that we're not doing definition checking, at least not till we learn something more about it and how to do it, because it will harm industrial infrastructure and performance. So basically, sorry for running over a little bit, more than a little bit, I guess. Generic programming is just programming, and we are approximating Alex's ideals of the most general, most efficient, most flexible representation of ideas. It's based on classical mathematics. You can read his books. It treats built-in and user-defined types uniformly: scope, naming, creation, cleanup, resource management. Complementary to object-oriented programming, not an alternative in all ways. There are concepts of compile-time functions. They specify what a generic function requires of its arguments and can be used to select among alternatives. So basically, it allows us to extend the C++ type system on top of what we get by default. And the example I started out with was not just a library, it was a type system that integrated runtime testing and compile time testing to solve a practical problem. Okay, thank you.
Great. We've got a couple of minutes for questions if you'll have a few questions. And a dead phone. Any questions? Hand up at the top, Simon. Not sure if the dare throw this over the top of all the laptops.
Oh.
Okay, so I'm not very good at catching. Do you think we'll ever get to the point where we capture units as well as types? So obviously if you've got, velocity might be miles per hour, kilometres per hour, metres per second, and it's very easy when using something generic to get mixed up.
I have not tried to apply concepts to the unit problem. We have a proposal for a unit library for the standard, and it is available as a library, and it's a general unit system. I've been using the SI system for maybe 15 years. It's not that hard to do even without this. You can download the unit library. I wouldn't be surprised if I couldn't improve it, but I haven't tried, so I would claim it.
Why did you decide to make concepts be sort of into booleans? It seemed that a lot of cases you had like annotated what the error meant, but it didn't seem you had that in the code. Is there a way to encode this, or is that just like a nature of how concepts have been implemented?
I had, I'm not sure about answering the question correctly, and you can correct me later. I had a version that was accepted for C++, an early version of C++ that introduced actions, which is basically first-order predicate logic. And we ran out of time and never got it back in again. But basically, I have not felt the need for anything more than booleans. The general idea is that are you an iterator? Are you a number? It's a question, and therefore the answer is a boolean. Asking it more things, it would complicate things. If you go to static reflection, you can ask any question.
Okay, I think I phrased my question incorrectly. I meant the errors you get out, basically. In your power of 2 and greater than 100 example, wouldn't you get like quite an arbitrary error from the entire expression? You couldn't, for example, type an informative message there?
The compiler writers are trying to do that. And the net effect is that their error messages are 20 times as long as mine. And the reason is that quite often the error happens once you call something, and they haven't quite figured out how to always get it up on top. When I, together with friends, built a compiler, there was a switch. And the default was what I showed you. This is not that. You hit the switch, and then it basically says because. But I'm not a compiler team for places, and they don't seem to think like that. Sorry, I want that too. I had it and I lost it.
Any final question? No, let's. One in the corner.
Bjarne, with Rust traits, you you get this really, really seamless transition from compile time to dynamic trace. Can you see concepts moving into the dynamic side of things, or do you see a block of that?
No, I don't feel the need.
Okay.
The point is that the really smooth transition there for computation is const expr. And here you're explicit about what you want to have done at compile time and what you want to have done at runtime. And at least for now, I think that is the right solution at scale.
Thank you.
Great. I think we're going to call time now, and if you have other questions you'd like to ask Bjarne, then please do come and speak to him afterwards. We've got tea outside afterwards now, so it's an ideal opportunity to ask him any more questions. Wonderful. Thanks very much.